The chain rule. Essential question. Do I recognize a composite function and can I find its derivative using the chain rule? Combinations of functions. We've been working with two functions that are the sum of two functions, the difference of two functions, the product of two functions, and the quotient of two functions. And now the next combination we're going to take a look at is a composition. Now, what is a composition and what does it look like? Well, it's where the input value is being put into a function, such as g of x, and after it goes through the g of x function, it comes out, and then it's being sent into another function, which this is now being sent into the f function, and we get this. And the procedure is called a composition because the new function is composed of two functions, f and g. So it's one function going into another function. All right, so what is the chain rule going to look like? Well, there are two ways we can look at the chain rule. One is this way, and this is the derivative. Here's the composite right here. And we know that g is the inner function for f. And so we're going to find the derivative of f in terms of the inner function and then times the derivative of the inner function. That's what the rule looks like. In Leibniz notation, it looks something like this. dy du, where u is the inner function, and then take the derivative of the inner function, du in terms of x, du dx. All right, so let's take a look at the chain rule and see if we can make some sense of it in a proof here. The inner function right here, we're going to find its difference because we want to take a derivative, so we're trying to find the difference between that. And then we're going to find the difference of the outer function right here, and that's going to be dy. Okay, so dy dx is equal to the limit as of delta y over delta x, and we can write delta y in this way, where it's the change in y in terms of the inner difference, and then the inner difference in terms of the delta x. The limit of a product is the product of the limits, and then these become dy du times du dx. So again, this is another way, this part right here is another way of saying f prime of g of x, because g of x is our u, and then take the derivative of the inner function g prime of x. So that's what it's saying. All right, let's go ahead and do a problem. So we go through this process right here. F prime of x is going to be the derivative of the outer function, and the outer function is, I'll say, root u. So let's say f of x is equal to root u. So it's the square root function that's the outer function, and u is just this part right here, the inner function. So I'm going to do 1/2, and I'm going to use the inner function, x plus 1, to the negative 1/2 power. So I'm using the power rule. This is a power rule, so I use the power rule derivative, times the derivative of x squared plus 1. So this is going to be 1 over 2 root x squared plus 1 times 2x. And I can simplify a little bit, and I will get this answer. Okay, let's go over to the calculator, and I'll show you how the calculator can check your work. I've put in the function. I've put in what the derivative is going to find the derivative, how the calculator is going to find the derivative, and now I'm going to put my guess. So I'm going to say x divided by, and then I'm going to write root x squared plus 1. Okay, now I know I'm right if the calculator's derivative and my derivative will have the same graph. And I think what I'm going to do is I'm going to go up here and I'm going to turn off the function. Over here. and I'm going to turn off the function, and so all we're going to see is the derivatives. So let's go ahead and zoom, and I'm going to do zoom standard. Here we go. So this is the derivative that's being graphed. That's the calculator's derivative. And here's my derivative, which is matching perfectly. So that validates that I did find the derivative correctly. All right, let's go ahead and do some other examples. Right here, the hardest part here is to make sure you recognize you have a composite function. And I see this. I see my outer function being the sine function, and I see my inner function being the x squared function like this. So y prime will be equal to the derivative of the sine function, which is cosine of the inner function, x squared, so that's what it's saying right here. Outer function, derivative of outer function evaluated at inner function, that's this, times, and now I'm going to take the derivative of the inner function, which is 2x, and that's how we do it. All right, over here, y equals, I'm going to write this like a composite function, sine of x squared. I want to recognize that the outer function is a square function, and that the inner function is a trig function. So that's kind of the reverse of what we had here. Here, our outer function was sine, our inner function was a power. Now our outer function is a power, our inner function is sine. So my y prime will be equal to, I'm going to use a power rule here, and I'm going to evaluate with my inner function, so sine of x to the first power times, now I'm going to take the derivative of sine of x, which is cosine of x. So this is what I'm trying to follow. This part is this, and this part is this. All right, now let's take a look at the power rule again. In here, the power rule combined with a chain rule. So our inner function could be something more than just x. So again, I'm going to identify my inner function, or my outer function. Y is equal to u to the 100th power. So my outer function is a power rule. My inner function is also a power rule, but it's more like a with two terms, a two-termed expression. So y prime will be equal to 100. I'm going to use my power rule. I'm going to be using the inner function, evaluated my inner function, to the 99th power. And so that takes care of the first part of the chain rule, times, and then the derivative of the second part, 3x squared. And you can simplify a little bit by multiplying these out. And that's about the best you can do. All right, let's take a look at this function and let's see how they go about doing it and make sure we understand what's going on. So let's rewrite this as a power rule. And so my outer function is f of x equals u to the negative 1/3 power, and then my inner function u is going to be this x squared plus x plus 1. So I'm going to take the power rule right here and leave it in terms of my inner function, and then take the derivative of my inner function. You can wait till the next step to do that. So here's my power rule, and then I go ahead and find the derivative of that expression. Here's another example of finding the derivative using the chain rule. Again, my outer function is a power rule, u to the 9th power, and my inner function is this quotient. So my first step is to use my power rule. So here I do it here, and then I'm going to take the derivative of the inner function. And notice I wait, I don't do it right away. And so I'm repeating the first part of the chain rule, and I'm using the quotient rule here, and then I simplify. All right, here's a more complex derivative here. Notice that we have a product rule. So the first thing that we notice is that we have a product rule. And as we're using the product rule, we're going to have to use the chain rule. So here is the first function times the derivative of the second, noticing that this is a composite function, a function inside another function. And then the second times the derivative of the first, and again, this is a composite function. As long as you have something inside something else, then it's a composite function. So we're going to go ahead and right here, we're going to use a power rule right here, and then we're going to take the derivative of the inside function. Over here, I'm going to have to use the power rule again, and that's right here, times the derivative of the inside function. And this step actually does the derivative of the inside function here, and here, and we can simplify and it looks something like that. Okay, let's go ahead and do a problem. Notice that my outer function is e to the u, and my inner function is a trig function right here. So the derivative will be equal to, now the derivative of e to the u is itself, so this is e to the evaluated with the inner function times the derivative of sine of x. And this equals e sine of x times cosine x. Okay, now this chain rule is going to allow us to have another derivative formula. So far we have not been able to find the derivative of 2 to the x power. We can find the derivative of e to the x power, which is e to the x, but not e2 to the x power. What we're going to do is we're going to take any base and we're going to rewrite it in terms of the of e. So notice that e and natural log are inverse functions, so we can take a and we can rewrite this. So e to the natural log of a is equal to a. So I'm rewriting a as this. And then I multiply the two exponents. So the derivative of a to the x is the same as this. And I want you to notice that this is a composite function. So it's a function inside another function. So it'll be e to the exponential, which is evaluated at the inner function, times the derivative of the inner function. Now, derivative of natural a to x, this is a constant. So it's like saying derivative of 3x is equal to 3. So this answer is going to be a constant. Here it is right here, and we can rewrite the answer here. So if I wanted to do 2 to the x power, it'll be itself 2 to the x times the natural log of 2. Now the derivative for e to the x works here as well. It'll be e to the x times the natural log of e, but we know the natural log of e is 1. And that's why, you can use the rule, but we already know it's e to the x. Okay, here's an example of using the chain rule. This is a function within a function within a function. So we just take them one at a time. The outer function here is sine, so we take the derivative of sine, leave the inside alone, and taking the derivative of the inside function, inner function. Okay, now we're going to take the derivative of the inner function. Remember, this is a function within a function, so we're going to take the derivative of this part right here. So we copy this from here, and then we're going to do the derivative of cosine, which is negative sine, in terms of the inner function. So that's this first part, but then you have to take the derivative of the inner function. And then this is the last time. So notice that we use the chain rule twice. Here's an example of differentiating with an exponential. And that's the end of the screencast.